So good afternoon, everyone. We're getting started. Today we welcome Krzysztof Lisiecki, who will be today talking about hunting for vipers, red nuggets, traces of the past. But first, he will be introduced by Sebastian Corral.
It's my pleasure to have invited Krzysztof, who is a PhD student in the National Center for Nuclear Research. And this is his first talk as a PhD student because he started his contract yesterday. So what he's going to present today is the work he did during his master thesis, which is actually published as far as I know. And please go ahead, and thank you for coming here.
Okay, so hello everyone. I'm Krzysztof Lisiecki, and I came from Poland. I've been working on Nicolaus Copernicus University in Toruń. Now I started my PhD at Warsaw, and I wanted to present you the results I get during my master thesis about the red nuggets, which are a very unique population of galaxies. So let's start with a brief introduction to the subject. So how do we gather information about galaxies? The first information usually we get about galaxies, the morphology, right? So we need one observation to see how the galaxy look like. What is the shape of the galaxy? And the studies about the shapes, the morphology started with the Edwin Hubble 100 years ago. I suppose most of us have seen this Edwin Hubble's classification fork scheme, which is dividing all the galaxies into the two main groups, first ellipticals and then spirals. And because of the astronomers thought that the galaxies evolved from the random elliptical galaxies to the spirals, until this day, until now, we still call elliptical galaxies early type galaxies and spirals late type galaxies. Of course, this is not the last study that we get about morphology of the galaxies. In the late 50s, in this work of de Vaucouleurs, we could see the lemon shape scheme, which introduces us more continuum changes between specific groups of the galaxies. There are no such significant difference between every group, so it's easier to find an evolution track for those. And of course, probably the one which had the most impact for current morphology studies, which is a Sarsic profile, which tries to describe the brightness profile of the galaxy and help us to understand what is happening inside this object. But this is only those information we can get from single observations, right? So what will happen if we will have two of those? We can introduce to the colors. So quick reminder, colors in astronomy are the difference between two brightness in the different bands, right? So we have to have observation in two different bands, check what's the difference between the brightness in both of them and see what the result, right? And right now we know that the galaxies we observe like to lay in two specific groups. There are two places on the color range that they prefer to be, and we call them we call it this phenomenon bimodality of the galaxies. And we know that some of the galaxies are more red and that red sequence, and some of them are blue and star forming blue cloud. And in between those two groups, there is something called green valley, where the galaxy evolves very fast, very rapidly through this from the blue to the red. And why do we call red galaxies red and dead? That's because those galaxies contain mostly very old stellar population, old stars. There is no much of the star formation processes, and that's the difference between red and blue galaxies. And later we found also that there is a correlation between red galaxies and spiral galaxies, and elliptical galaxies, and the blue and spiral galaxies, of course. So now we know that the shape of the galaxy also gives us a hint about the star formation processes inside it. It's not full information about it, but it also gives us something. So what's the next point with gathering information? So we can get a spectra of the galaxy, right? And for me, the most important part of this is getting a redshift. So the information about how far the galaxy is, how much time it's been since the light were emitted until we get it on Earth, right? So it allows us to estimate the sizes of the galaxies, the absolute magnitudes, which also influences all the estimation for physical properties and every single estimation, actually, what we do about the galaxy. So it's crucial for almost every single part of studying this particular source. But of course, it's not the only reason why we want to have spectra of the galaxies, right? We can also get an information about the metallicity of the galaxy, about the stellar population, about the ages of the stellar population, as well as, of course, a few hints about star formation processes again, which is also used in this work later. And the last thing, if we would have enough time and enough money to get a full spectral energy distribution from high energies to the radio part, we would get a full spectra of the galaxy for every single sources. We could try to recreate every single physical properties and physical parameters within this object. Of course, we cannot do this for every single galaxy on the sky because it's simply impossible with the resources we have. But using a multi-wavelength photometry, we can try to recreate a full SED from a few observational points, right? So here is a good example how different bands influence the estimation of every single physical properties of the galaxy, starting from stellar masses through the star formation rate, through the dust, metallicities and ages. That's all can be read from the SED. And using the science that we already know, we can try to recreate the SED from few observational points. Okay, so let's move to the red nuggets. What are they? So those are very extremely unique galaxies, very compact and massive, and also this part red stands for the passive galaxies, right? So ultra compact massive galaxies which are also passive. This is what we are looking for. So to find a red nuggets within a survey of the galaxies or within any sample of the galaxies, we need to focus on three things. First of all, those galaxies have to be quite massive, at least 10 to the power of 10, depending on the criterion we use. And you can think about it like, well, it's not the most massive object we know, right? Even our Milky Way is like 10 to the power of 12. So they are not very very massive. But if we will think about it, like those galaxies were originally observed at high redshift, so they had very little time to gather that much mass, and they had to do it in very short period. That's already quite special. And combining it with very small sizes, less than few kiloparsecs. For me, for example, I was looking for galaxies less than 1.5 kiloparsec. So the density of the matter within the galaxy, within that such red nuggets, is a few times higher than the density in our galaxy, for example. So they are still unique and still very interesting objects to study. And the third part of looking for those objects are, of course, the star formation processes. So we are looking for objects with low star formation rate and old stellar populations. Of course, they have to be red. They have to have no features of any star formation rate. This is what I've been looking for. And if you would like to know why they are so special and why they are so interesting, you should take a look at the so-called two-phase scenario of how the galaxies, elliptical galaxies, were born and evolved through the redshift, through the cosmic time, let's say. So the first phase of this ends when the red nuggets are formed. They are actually already compact and massive and also passive. And the second phase is are only mergers and interaction with other galaxies to gather more mass, and they are just growing in size as well. So this is how the most massive, the biggest galaxies, elliptical galaxies in the local universe were made, were born and evolved through the cosmic time. But we have to know, we have to have in mind that the merger processes are stochastic events, right? So we can suppose that some of those red nuggets, which were born at the end of the first phase, can survive without attending the second phase and keep the size and the mass almost unchanged, untouched through the last few billions of years. And they end up as a so-called relic galaxies in the local universe. And they are very good objects to study extremely old star populations, which were not influenced by any other galaxy, by any merger, by any interaction. And also it can give us a hint about the environment of early universe as itself. So of course, not every single red nugget is a relic galaxy, right? But they are the best candidates to find among them the relics. So here is an example. How do we look for relics? We have to study the stellar population and the mass, how the mass were added to the galaxy through the time, through the lifetime of the galaxy, let's say. And we have here two examples. One of those, when on the left, we can see this is the most extreme relic that we can probably find. All the mass was born in one single star formation process, one star formation event, and then it didn't change through the last, I don't know, 8-9 billions of years, as we can see from this plot. And the second one, it's a bit more complicated. We can see that there were at least 2, maybe 3 star formation events, but it's still a good object to study. So we are looking for red nuggets to maybe in the future find a few relics among them and try to study them. They are extremely rare. That's the reason why they are so interesting, right? So let's move to the data which I used. So I've been working with the VIPERS, which is Vimos Public Extragalactic Redshift Survey, which was originally designed to study the spatial distribution of the galaxies at above redshift 0.5. So here is a comparison with the SDSS, and we can see that we are going much deeper, much farther than the SDSS. And of course, for the obvious reasons, we cannot go as wide as the SDSS. We don't have enough time and money, of course. But it still gives us an incredible number of sources, 90,000 galaxies with spectroscopically measured redshift, which is crucial for this study, and also many other studies. So those 90,000 galaxies are at redshift 0.412, and we have optical spectra for every of those objects. Within the VIPERS, we also have multi-wavelength photometry, starting from UV to the infrared, Galaxies, Canadian Fringe, Hawaii telescope, Vista-wise Spitzer, and here are pictures borrowed from Wikipedia of every single telescope that were used to this. So we have from UV, we have observations from UV to infrared, which is useful for SED fitting, of course. The most important part of this survey is that we have those redshifts, right? So for 54,000 galaxies, we have redshift measurement with confidence higher than 95%, which allow us to make to do studies at higher redshift than SDSS, and also a good significant with a good statistical power. Because we have the spectra from the optical part, we always can, no matter which redshift we're observing, we always see this part of the spectra where are a few features indicating against star formation processes like O2 emission line and calcium H and K absorption lines, D4000. So many features that can be used in the following analysis. In addition to the observation, I also used the morphology derived by Krzysztof et al. In 2017. During their studies, they used Galfit with usual Cerstic profile fitting. And for me, the most important part was getting a half light radius, which is for me effective radius of the galaxy, which is how I measure the size of the galaxy. And the last thing, is that the VIPERS team tried to calculate the stellar masses of the galaxies. Unfortunately, they do not give us the information about the uncertainties. So I decided to recalculate stellar masses and other physical properties to give a scientifically important result, of course. So in this part, I used code investigating galaxy emission, which is SIGAL, which allows us to model SED of the galaxy we are observing. We are giving SIGAL all the observation of this, all the multi-wavelength photometry. We are giving the redshift, and we are giving a few parameters which we are trying to guess which of those physical properties should our galaxy have. So you can think that this is just a guessing how the galaxy should look like, but it's more like a scientific guess. We know how the galaxies work. We know how every single component emits light, how it should work within the galaxy. So it's more like a scientific guess because someone very wise did it before us. Someone studied the initial mass function. Someone studies the star formation histories, and someone studies the metallicities and the dust and everything that is included into SIGAL. And it allows us to recreate the possible SED of the galaxy. At this point, I also tried to check a few models that are included into the SIGAL. So here is a comparison of my result of the stellar masses. And the difference is that in one calculation, I used the shallow and fall model, and in the second one, Scalzetti. And as you can see, they are not the same. There is the difference around factor of 2. But here again, first of all, we have to know our sample at least pretty good to know which one fits better to our sample, which one should we use, which one will better describe our galaxies. And second of all, we have to have in mind that they are not 100% sure. We cannot be sure that they are perfect. So let's move to the analysis. I started with pre-selection of the sources. So because the size of the galaxy is one of the 2 or 3 parameters that I really use, I wanted to be sure that my sizes estimations are at a very high confidence. So I also use the only galaxies with at least 95% confidence in redshift estimation. In addition to that, I also focus only on galaxies between redshift 0.5 to 1, and it is due to the color success rate. I wanted to be sure that we are at least pretty sure that we are complete in color. Here is a plot that shows the reason why we did it. Color success rate at 0.5 for passive galaxies is around 0.8, which is, let's say, enough. And the cut at 1 is because at 1 we are very close to reaching the mass limit, the mass completeness as well. So this also was important for us. And the third criterion was to have an effective radius uncertainties, because GalFit is only an algorithm. It can have encounter a problem during the fitting. It can not give you a very good fitting, high p-squares or any other problems. We wanted to be sure that our estimation are the best of the best, so we focused only on those 36,000 of galaxies. Okay, so we've got those 36,000 of galaxies, and we wanted to find ultra compact massive galaxies. So here we encountered another problem, right? Looking for those galaxies and studying them is a relatively new field in astronomy. There is still discrepancy which galaxies are called ultra compact and which are not. There are many different criteria in the literature that you can find. For example, here you can see that using the most restrictive one and the least restrictive one gave me an result different by 2 orders of magnitude. So those population of galaxies, those groups of galaxies are not the same. We are not comparing the same galaxies. So it implies that when we are trying to compare our result to another study, it is not straightforward, right? Because they can study a bit different population of galaxies. And the second of all, we have to know our sample, again, at least pretty good to know which of those criteria fits the best for us. I wanted to focus only on the most massive and the most compact galaxies, and also I know where the mass completeness limit lays in my sample. So I decided to use the most conservative criterion, 3Ho 2009, which is just 2 simple cuts, mass higher than 8 to the times 10 to the power of 10 solar masses. This is, of course, the dark Turkish eye of evil, but I couldn't find the although sign in my slide maker, so sorry for that. And the size smaller than 1.5 kiloparsec. So I ended up with 86 sources, which I consider an ultra compact massive galaxies. But if you find a paper when someone is studying ultra compact massive galaxies, those maybe different population of galaxies. So we have to have it in mind. So we have ultra compact massive galaxies. So what do we need to find a red nugget? We need to know which of those galaxies are passive, right? So again, we don't have a direct information how many stars are born in this particular galaxy during 1 year. So we don't know what is the star formation rate of this galaxy from direct information. We can, of course, try to estimate it from the SED, and as well, we can use other hints about the star formation rate. So here is, for example, one of those hints, which is a color. In this example, color diagram, Nufer K, which is widely used by VIPERS team. We even have a criterion for separating red sources from blue sources, derived by Thibaut Moutard in 2016. As you can see from those 86 sources, 7 of them lay below this limit, so I removed them from my sample and went to another step, which is looking for every single spectra of those galaxies, of those 79 galaxies within my sample. So I've been looking for very specific features which may indicate that in this particular galaxy there are some star formation processes. So here you can see a comparison of two spectra. The top one is possibly active galaxy. The bottom one is possibly passive galaxy, and the differences are, of course, the emission line of O2 and lack of absorption line of calcium, and also the low Balmer break value. And in this step, I found next two galaxies. So I ended up with 77 red nuggets candidates after this. And the last criterion I used was checking the comparison of the star formation rate calculated through the Seagull to the so-called star formation, the main sequence of the star forming galaxies. So this is the relation which basically can give you a value of star formation rate at a given redshift for the given mass galaxy. And as you can see, all of those 77 galaxies, the red nuggets candidates, lay below main sequence, even including the uncertainties. So we can consider them as a rather passive object. And from this moment, I also, in my paper, consider them as red nuggets because I checked all the symptoms that I could. Also, here's another limitation. I checked a few more. If you want, you can ask me about them later. They are not very important now. And the last sanity check, let's say, was looking at every picture of those galaxies. So if there are any symptoms of structures of any kind, and those are very small objects at high redshift. So it's rather hard to see anything in there, but it was good to check it at least. It's not impossible for those galaxies to have any features. Okay, and as a result. So for me, the most important result is that I established a new catalog, previously unknown 77 red nuggets, which were not only confirmed spectroscopically, but also they were selected spectroscopically. So I had a very good sample from starting. Here is a distribution in the redshift of those galaxies. As you can see, they are not evenly distributed. So when I tried to, let's say, study a few physical properties or few statistical properties of this population, I divided them into four simple bins. I wanted to have a similar number of sources in each bin, and also the last bin is slightly below our mass completeness, and that's why it's also at 0.9, but you will see it in a moment. So first of all, nothing very interesting. I found now not significant relation dependence of the D4000 or the stellar mass of those galaxies. They're just constant almost through this redshift which I studied. Here is another star formation activity limitation from Kaufman 2003, and here we have 6 sources which even with uncertainties lay below this limitation. But again, the Kaufman limit were derived for a low redshift galaxies in the SDSS, so we can suppose that at higher redshift it could be a little bit lower, and that's why we didn't remove those galaxies from our sample. But it's good to have in mind that they are a bit stranger than the others. And the second most important result of this particular study was to calculate the number densities of those galaxies. So we wanted to see what is the probability to encounter this galaxy through through the given volume, for example. So here is a comparison with a few studies that were studying the ultra compact massive galaxies, most of them. And first of all, as I said before, it's not straightforward to compare our result to them result as long as they're not using the same criteria. So at lower redshift, those two studies used very similar criteria as we did. So we can compare our results with them. So we can see that our results are in great agreement with them. We have the same trends, the numbers are pretty close to each other. We get different starting samples. So this is something that we have to have in mind, of course, because we have, from the beginning, we had spectroscopically measured redshift. They did not, at least the Damianov did not, and they are also Sconamilio did not. They get the redshift after finding the candidates, so they confirmed it. We had it from the beginning. So we are in great agreement with low redshift studies, but on the other hand, at high redshift studies, it is very hard to compare because both of those studies used critically different criteria. And the only thing that I can say that we are in overall good agreement because we lay somewhere in between. There is no much to say about it. Okay, and the second part of our study, the more recent one, is about the checking if our red nuggets have any environment preferences. Do they prefer to be in high density places close to the nodes or in the filaments, or do they prefer to be in the field? And this is still an open question because we don't know if those galaxies would rather evolve isolated in the field or in the very dense objects like the nodes, for example, or the group. So to characterize the environment of our red nuggets, we generated those three control samples, all the red nugget, the red VIPERS galaxies, similar mass and larger sizes, also red galaxies, similar size, smaller sizes, also red galaxies and our red nuggets. And our results show that there is no significant relation between finding a red nugget and environmental preferences. We found almost the same number, those galaxies in high density and low density space. And in addition to that, we found the most similar distribution of red nugget galaxies is the one with similar sizes and lower masses. So we can try to compare the evolution of red nuggets with those galaxies. It is of course the different population of galaxies, but we can try to somehow connect them in the future studies. And of course, it's not the end of this project. As you know already, I started yesterday my PhD, so it's probably going to be my project for a few years at least. And we have few ideas. Of course, if you have any more, I would be happy to hear them. But we would like to study individual galaxies of those red nuggets. Of course, they are quite interesting. We have 77 objects, so we could try to study the statistical parameters of those groups. Looking for relics is the first thing that we have in mind. And also during the analysis, we found some of the sources which are even more interesting than the red nuggets, which we don't know if they are nuggets but not red, but or are they any other kind of the galaxies. So we would like also to check on them. yeah, and many others. The environmental thing is also interesting. And as the end, as a summary, I would like to show you this beautiful plot made by Gosia Shudek, which shows how those galaxies can evolve through the redshift within the cluster or in the field. With mergers, without mergers, they can be everywhere. You have to watch out for them. And I would like to thank you for your attention now.
Thank you, Chris, for your talk. Now it's time for questions. We start with questions from the aula, from the room here. No, I have not pretty far from this, but I have myself some questions. If I understand what makes these type of objects so special, that they are very massive but compact,
yes,
and that they are thought to be generated at very, very high redshift.
Yes.
How old are the population, the star population of these objects?
So I didn't study my population yet, but we suppose that they should have a population of about few billions of years.
Few billions of years.
Yes.
Okay.
Because we are at redshift 0.5, so 1. So it is like 5 billion years ago, right? So
so very high redshift.
3 to 5 billion years.
Okay.
That would be great to find a relic.
I see. I see. And then when you were computing number densities, these are a spectrum, right? These are VIPERS. These are Viper galaxies. So they had to be pre-selected somewhere to put a fiber on those.
Yes.
Okay? Do you know how this pre-selection could impact your estimate of the number density?
Yeah, so that's a very tough question. I know how the pre-selection of the VIPERS were made. There were some cut on very rough cut on the I band, but it should not influence the result very much because we are still focusing on the most massive galaxies. So we are very, very close to the limit, the completeness limit, right? So it may influence a bit, but our results are rather close to complete. Yeah.
I see that there is at least one question in the chat. I think it was from Javi San Roman. Javi, if you can talk, go ahead. If not, I will. Let me just read your question, okay? So you can read it yourself. Did you use PSF deconvolution to measure, to measure the effective radius given the low apparent sizes of such high redshift galaxies?
So yeah, I read the Krzysztof et al. 2017, and they used PSF deconvolution. They get the PSF for every single source separately. They didn't use one PSF for all the field they used. I have to say that during my let's say exchanging emails with referee, the referee were asking a lot about Galfit, and I'm not into Galfit yet. So I'm not sure how this PSF is working within the Galfit, but I know that it was used there. And it is a problem that some of those galaxies are smaller than the size that our telescope should be able to see. But if they are smaller, that's not a problem because we are looking for small objects.
Okay. Okay, Sebastian, I'll hand the mic to you.
You said that you see no correlation between the relics and dense environments, which, well, the literature seems to indicate that not everyone agrees, but most of the people seem to agree that they should be in dense environments. So you seem not to agree with that. There's another paper which says the same. So you are not the only one. Can you comment a little bit on that? Have you, or?
Okay, so I said that we do not see any significant relation. So we found almost the same number in the dense environment and the low density environment. But it's still an open question because we have only 77 sources and almost half of it was removed because we didn't have any information about the environment, right? So in this distribution, there is like 44 sources, I think. So 10 of them is in low density, 10 of them is in high density. But of course, it is already a result, right? So
can you go to the previous plot?
yes.
Have you done a Kolmogorov-Smirnov test or something similar?
Yes, they are in here.
Yeah. Okay, those
yeah,
are the
but
numbers. Okay. That's what I thought. Okay.
Yes.
So they are very similar. Yeah. Okay.
Okay. Did you obtain metallicity estimates from the spectra? Can you use new spectroscopy to constrain metallicity of an enhancement? Okay, so we didn't work with metallicities yet. There is an idea to do it. As we have spectra, it should be easier. I even write in a proposal to do it in some kind. Of course, the near spectroscopy would help us a lot to constrain them. And about alpha enchantments, it's hard to say about it because I didn't start working at this field yet. I think this is a good idea to start. This is a good idea to continue, but I don't know yet. So yeah.
Okay, thank you, Chris. All right, so unless there are more questions, I think it's time to thank Chris for his talk again.
Thank you.
And then we can wrap up here. I just remind PhD students that they should sign up here in this piece of paper before they leave.